Well, good morning. We're very fortunate to have Pablo Enrique Moreira from Galván from Mexico talk to us about ambient temperature modeling with Newton's law of cooling using sensors. And of course, he is fortunate enough to be in a much warmer climate than we are in North America at this time. But sensors and temperatures all work the same. So we're looking forward to hearing from you, Pablo.
Thanks. So I'm going to talk about the modeling the ambient temperature and the Newton's law of cooling. This is a work with my colleague Oton. We are from Anáhuac, Querétaro, Mexico. So we have the motivation, the principal motivation was the students to apply in real world application, because in the textbooks are really weird, the application. So we need to connect the theory with the examples. We need to engage the students because the students in this time doesn't want to learn differential equation. And for me, this is the point more important, because the students doesn't see the relation between the real world experience and the theoretical solution. So we make this experiment in class. We take a sensor, we make the experiment, and we see that the solution is exponential, blah, 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 blah. And one student tell me that doesn't make sense, because as we seen, the solution for T large doesn't make sense, because in this case, the water needs to change in the time. In the hottest day of the day, we have a temperature. In the night, we have another temperature. So doesn't see in the solution. So we do this experiment. For me, this is the more important thing. And the University of Anáhuac tell to all the teachers, they support the experimentation and use real world cases. So the Newton's law of cooling states that the rate of change of temperature of an object is proportional to the difference between the object and the surroundings. So we express the equation. So we need to solve this equation with this initial condition. So here AS is the surrounding temperature, and K is a constant of cooling rate. This is the easiest example that we see in differential equation. So I solve this equation in the following way. So we multiply by this factor. The left side is the derivative of the temperature and exponential. So we need to solve this equation for T. So we need to integrate to 0 to T, and we find that the temperature is given by this expression. So only we need to find an expression for the ambient temperature. So the room temperature in our case is linear, because we take data in 9 hours, or is quadratic. We take data from 0 to 18 hours, or is a wave. We take data from 9 hours, 18 hours, 2 days. So we say where are which of these models is the correct. So we solve this equation for all these expressions that see. And in the university have a weather station, so we take the model for 6 days, and as we think, it's like a sine wave, but those here and here are different. So we think that it's a damped sine wave. So for the first example, we take the room temperature. Here is the graphic. In this example, only we have one sensor like this, so only one. So we take this data. We propose this function because we think it's a wave. So take a day, the 0 to 24 is this expression. We start at 9 p.m. and we have 1 day. So it's easy to see to the students that this is a wave, this is a sine. Only we have to display one displacement upward and right or to the left. So we have this expression for this data. So 1 day take this, well, over 2 days we take the data. The next day we have the example. So remember the equation to solve is this. We solve with the constant model. In this case is we start with 25, 24 degrees. So with the constant model is this. Only replace constant here, solve the integral, and you are able to find the temperature is this. And also it's easy to calculate K. K have this form. And we use a wave and replace here, solve the integral, and we have this expression. So we start at 6 p.m. The initial temperature is 20.5 degrees. We have 50, like two days, a little more, a little less. I don't remember. I think this is the correct. And the ambient temperature is in 3-degree range. Here we see is a 3-degree range. We add, so we need to add this P/4 because we take the data at 9 p.m. It starts to 6 p.m. So we need to adjust these parameters. So we need to add this expression. Because we have 3-degree range, we need to add this 1.5. Remember that sine is between -1 and 1. So we have 25 and 22.5. We have this table with some time and the temperature, and we consider 100 to find K. So the ambient temperature is this, and for the wave is this expression. So this is important thing because if you consider T large enough, this expression is like 0. This expression is like 0. So if you consider the constant, we have the temperature is like 20.5. Instead, if you consider a wave as model, we have 24 and this trigonometric function that give us the change that we are looking for. So these are more accurate model. Here is the data for over 2 days. The blue part is the real data. The red dots as the ambient when we consider a wave, and the pink dots are the if you consider a constant model. And as we see, the experimental model and the sinusoidal model is almost the same. We have the error. The orange part is when you consider the wave model for the temperature, and blue is the constant model. As you will see, is more accurate when you consider a wave, a wave like a model of the room temperature. So these points of the highest error is here. I see, is like this. See, our model is there, and remember that for t large enough, the constant model is like a constant. So we have the constant is the reason why we have, is why this, our model is more accurate than the constant model. So we have an important thing is that for t large enough is 24.5, that indicates that the ambient temperature is never reached based on this model. If you consider, for example, 25 to 24, excuse me, in the constant model, you never can obtain a temperature under this point. Instead, with the variable model and with the aid of MATLAB, the ambient temperature can be reached approximately in this method. So in this example, for my students, give a different times, lapse of times, because we are to predict the room temperature in different lapse of time. For example, to 0 to 6 is like a line. From 0 to 15 is like a quadratic function. To 0 to 25 is like a wave. So depending on time to be considered, they accept different modeling approaches. So we have these approaches in different lapse of times. The constant, linear, quadratic, cubic, sinusoidal, damped sinusoidal, and some of a student, they think this part from 9 to 25 is like Gaussian. So we accept these models. We graph the model and the temperature. They are the graphs. For example, the quadratic fit is really close to real data from 0 to 15. The cubic fit also is really accurate, and a damped sine fit. Damped means an exponential by multiplied by a sine. So we use these models to substitute to find the temperature. For example, let's consider the linear model. Remember that we need to substitute this function in the integral. This is an easy function to integrate. And we are use data, this data to find K. So K is the solution of this equation, and this K was obtained with aid of MATLAB. So this is the reason that I think the books doesn't use models like that, because if you consider K in the constant model, it's easy to find. You have an expression that involves logarithms, but in this case, K is necessarily find. We need to use MATLAB. In other cases, it is difficult to find a K that solves this equation. So we see that these have a solution because we graphed, we use the mean value of the function, some of mathematics, but this, for me, is impossible to find an analytic expression for K. So I think this is a good reason that the books don't use that, but in this case we use, and we have for this room temperature, we have this expression of the temperature function. We have the graphs. The blue part is the prediction, and the orange part is the real data. For example, the cubic feet prediction is really accurate, and sinusoidal function also is really accurate. We think that this is almost the same, because if you expand sine in terms of Taylor series, we have a cubic function. So as you will see, if you use different models to room temperature, we have these approximations. So quadratic function, for example, is really good from 0 to 15 hours, and sinusoidal function from 0 to 25 is really good approximation. But linear approximation doesn't make sense. From 6 hours to 25 doesn't make sense, but from 0 to 5 is really good approximation. So if you want to use this data from these experiments, we have this drive, or if you want, you can send an email. This is my email. Also, these are published in these journals, Revista Mexicana de Física and Physics Education. They have open access to data. So if you have any questions, I'm ready.
Thank you very much, Pablo.